Hey class, back now after exam 2. We're going to be starting, today we're doing lecture 23, which is beginning material for exam 3. Just to remind you all, there are 3 midterm exams and 1 final exam. So the third midterm exam and the final are pretty close together. Just check the schedule for that. But the third exam, like the exams up to this point you've probably seen will mainly cover the material for that exam. For example, like exam 2 was mainly chapters like 12 through 22. Or sorry, not chapters, but lectures 12 through 22. Exam 3 will mainly be lectures, I think it's 23 through like 32 or something like that. And then the final will be more comprehensive, giving more of like an equal shot at any lecture from the start of the semester, basically. So, but you can also kind of see how the ideas build on each other as we're going throughout. So we're going to continue to build on the ideas that we've done before and adding to that stoichiometry map, and hopefully I'm trying to keep the ideas as, I don't know, tied together as possible so it doesn't seem like too much new information as we move along. But let's go ahead and get started here with this lecture 23. Okay, so go ahead and take this quiz here. All right, so the quiz says, which of the following would you expect to be most soluble in oil? Okay, so we're going to start talking about solutions and the solubility of different compounds in water and stuff like that. So the main idea here to remember is that like dissolves like. So what that means is nonpolar liquids will dissolve nonpolar liquids, and polar liquids are more likely to dissolve polar liquids. So if you draw out the Lewis structures for all of these, we have hydrochloric acid, which is definitely polar. Okay, you have a polar bond. Ammonia, the nitrogen-hydrogen bonds are not very polar. Are polar. That's what I meant to say. And so you have a pretty good polarity going on in this molecule. Water definitely has polar bonds. It's very polar. The nitrogen-chlorine bond, you can tell here nitrogen and chlorine have the same electronegativity. So these are non-polar bonds between the nitrogen and the chlorine. Overall, I would say this molecule still has some polarity to it because there is a lone pair. But basically, this has the most non-polar bonds in it, right? All these have very polar bonds. So out of all 4, this would be the most non-polar molecule on that spectrum of polarity that we sometimes talk about. Okay. And so since it's the most non-polar out of the 4, we would say that it is going to be the most soluble in oil, right? Because oil is a non-polar liquid. So the most non-polar molecule will be soluble in oil. And the same would have been true for, a polar liquid. It would be the opposite, right? The most polar molecule is going to be the most soluble in the polar liquid. Generally, we'll talk about some exceptions in the next lecture. Okay, so what we've done so far, and this is kind of our stoichiometry map broken down. So reactions with solids and liquids, we've gone from grams to moles, right? And then from moles of A to moles of B, right? And moles to grams. So we go between grams and moles using the molar mass. We can go between volume in grams to moles using density, right? This is all on that stoichiometry map. We've talked about gases, how we can use the volume, pressure, and temperature to go to moles, also on the stoichiometry map. What we haven't added into that map yet is reactions with solutions, okay? So going from solutions, which we're going to talk about in this lecture, over to moles, okay? And I'll update that map once again after we talk about, maybe in the next lecture or two, after we talk about kind of what a solution is first off. So biochemistry, which is probably what most of you are going to be more interested in, and you're going to study more in Chem 285, all happens in solution. Industrial chemistry, so making chemicals like companies and stuff, also happens in solution. So really, pretty much all reactions that are useful are going to happen in solutions. So we really need to understand the solutions. So what we're going to be learning about is solution properties and solubility of different compounds in a solution. And then how we can work with those reactions using like stoichiometry and stuff. Okay, so this figure basically shows what a solution is. So a solution contains a solute and a solvent. Okay, so you can see solutions consist of a solvent and, solvent and solute. I think I said that right. Another definition of solution would be a mixture of two or more substances. So like salt water, for example, like you see here, is a solution because it's a mixture of water and salt, right? That's two or more substances. But another way to think about it is you have a solvent and a solute. So the solvent is going to be the liquid, generally, the liquid part of your solution, generally, is kind of, I think, the easiest way to think about it. And then the solute is what is being dissolved in the solvent. Technical definition, I guess, would say the substance that is in greater amount is going to be the solvent. So obviously, there's more water here than salt. And so salt is actually the solute. There's less salt and it's being dissolved into the water, okay? So that's kind of how you think about a solution, basically. So solutes, once they're dissolved, they're going to spread evenly throughout the solvent. So the salt would spread evenly throughout the water. You can't filter them out because they're totally dissolved into the water, right? So you imagine pouring salt water through like a strainer or something. It's not going to do anything. It's going to come out salt water still. And they're not visible. So you can't see any kind of like particles or anything. If you put salt in water and stir it around and wait for a while, it's going to dissolve completely. And it's just going to look like clear water. Solutes can impart some color to a solution, although it would just look kind of like a transparent, color, like a transparent orange or something like that. But you shouldn't be able to see actual particles inside the solution. Okay, that's just kind of a general overview of what a solution is, if you were confused on that still. All right, so here's a demo that we generally do, and I'm not doing it right now, obviously, but basically what happens is we have salt, and the salt gets dissolved in the water, okay? And then we also try iodine, okay? So iodine would look like this, right? Lewis structure, and it would have a bunch of lone pairs around the iodines, and it gets dissolved in the carbon tetrachloride. So carbon tetrachloride, if you drew out the Lewis structure, you'd be able to tell that this is a non-polar molecule. So it's a non-polar solvent. This is the solvent. And then your solute is your iodine, which is also non-polar, right? It's just an iodine with another iodine, diatomic. And this is really just showing that like dissolves like. So non-polar substances like iodine will be dissolved in non-polar solvents, and polar, which ionic would be considered really just like a very, very polar molecule, would dissolve in solvents like water, which is polar. It's kind of a review there of the quiz question that we talked about. Okay. All right, so water is pretty much the major solution for all chemical reactions in the body, because we're made up of largely of water, right? And so we're going to be mostly concerned with water solutions because that's, yeah, pretty much what you're going to be studying. In Chem 285, you're going to see some reactions that are happening in non-polar solvents. But they still emphasize water again because most biochemistry occurs in water. So anyway. All right. So we're going to talk about electrolytes now. Sorry, I'm tired. So this is a demo that I generally do in class. So basically you take a light bulb and a positive and negative wire coming off the light bulb, and there's like a battery basically that's like going into the water. Anyway, and what it's doing is sending current through the water, and then you put the light bulb in, connect it with some wires and stuff. And what happens is if it's pure water, then the light bulb doesn't light up, which basically says that pure water is not a good conductor of electricity, okay? If you put sodium hydroxide in the water, there's going to be light. The light bulb's going to light up very strongly. If you put methanol in water, there's no light. We try acetic acid and there's a little bit of light. Okay, so really we're just, you try all these different substances and we point out basically the important thing here is that methanol gives no light, acetic acid gives a little bit of light, and sodium hydroxide gives a lot of light. And it kind of just leads us into the next slide, which we're going to be talking about electrolytes. Okay, so strong electrolytes produce ions, right? A strong electrolyte is going to be something that dissolves in water. Okay. So something like sodium chloride, table salt, right? It completely dissolves in water. So it's a strong electrolyte, okay? Anything that dissolves completely in water is a strong electrolyte. So sodium hydroxide from the slide before, it's going to be a strong electrolyte. If the light bulb is bright, that just basically the brighter the light bulb, the stronger the electrolyte. So anyway, don't worry about that too much. Just kind of worry about what I'm saying here, that strong electrolytes produce ions and conduct a current. And strong electrolytes are molecules that dissolve in water. Weak electrolytes produce only a few ions. So you can kind of see how this light bulb is a lot dimmer. Okay, so things like hydrofluoric acid, or HF, are going to be weak electrolytes. Okay, they're not going to completely dissolve in water. You can see how there's some HFs that still are together and some that actually split up into hydrogen and fluorine ions, compared to this one on the left where all the sodium chloride splits up into ions. So weak electrolyte, it produces a few ions, so some of the molecules split up, and since it's only a few ions, the light bulb is dimmer, right? The more ions, the brighter the light bulb, okay? And then non-electrolytes are things that do not split up at all. So if you put sugar in water, it's not gonna separate into ions or anything like that. You're just gonna have a bunch of sugar molecules floating around in the water, basically, okay? And so this would be, let's see. So for strong electrolytes, something that completely, I shouldn't say dissolves, sorry. Erase that word in your notes. What I meant to write was dissociates, okay? So something that completely dissociates or separates into ions is a strong electrolyte. Okay, a weak electrolyte produces few ions, it partially dissociates, okay, in water. And then non-electrolytes, they do not dissociate. So like sugar doesn't dissociate into separate ions. That's kind of what that word is meaning. Okay, sugar does, the reason I had to change that is that sugar does dissolve in water, right? You can get sugar to go into water, but it doesn't actually dissociate into separate ions. Contrasting that with the strong electrolytes, which actually dissociate into separate ions, okay? And that's the difference there. And then weak electrolytes are things that partially dissociate. So you kind of have this, spectrum between things that don't dissociate at all, things that fully dissociate, right? And the farther to the left on the spectrum, the stronger the electrolyte. Okay, so just kind of remember those concepts, that things that fully dissociate are going to be strong electrolytes. Things that partially dissociate or produce few ions are going to be weak electrolytes. And then non-electrolytes do not dissociate at all, so no ions are formed. And you can see that the light bulb doesn't even turn on in this example. Okay. All right. Okay, so again, like I said, strong electrolytes completely separate into ions, or dissociate would be another word for that. So an example of those is sodium chloride, which we've talked about quite a bit so far. Completely would dissociate into sodium and chloride ions. Calcium bromide would completely dissociate into calcium and bromide ions. Okay, so we're going to talk a little bit more specifically in the next lecture about what compounds completely dissociate in water. So anyway, don't worry about this too much, because I'm going to go over what compounds, exactly what you'll need to know in the next lecture. Right now, I just want you to understand that strong electrolytes completely separate into ions, okay? So there's some ionic compounds that do this, and there are many acids and bases that do this as well, that we'll talk about in the coming lectures. Okay, so weak electrolytes dissociate only slightly in water. Again, we said these will partially dissociate or partially produce ions. So HF is going to produce, we haven't really learned this yet, but H3O plus is basically the same as H plus. So it's basic. So HF will produce some hydrogen ions and some fluoride ions, but you can see these arrows right here denote that it's in equilibrium. So there's going to be HF present, there's going to be hydrogen and fluoride ions present, right? So it's not going to totally dissociate. Same thing with ammonia. It doesn't totally form ammonium ions and hydroxide ions, only partially. So again, that's just kind of the main idea that I want you to know right now. And we're going to be talking about more specifically what is a strong electrolyte and a weak electrolyte in the coming chapters or coming lectures. Okay, and then non-electrolytes, they dissolve as complete molecules. They do not dissociate at all. They just, the whole molecule gets dissolved into the water. They do not produce ions in the water. And so as a result, they don't conduct an electric current. So this is generally like sugars and alcohols. We won't see these as much in this class, but you'll see more sugars and alcohol molecules in Chem 285. Okay. All right. So one other thing to glean from this lecture is going to be what an equivalent is. And these are useful because, like, if you're going into nursing or anything, a lot of the IV fluids and stuff are defined by the number of equivalents. So an equivalent is just 1 mole charge. So a positive or a negative charge is a way to I think the easiest way to think about it. So if we have 1 mole of sodium plus ions, that equals 1 equivalent. Okay. 1 mole of chloride ions is 1 equivalent because there's 1 charge on the chloride. Now, if we had 1 mole of calcium ions, we actually have 2 equivalents because each calcium ion contains 2 positive charges in it. So 1 mole of calcium 2 plus ions is 2 equivalents. 1 mole of iron 3 plus ions is 3 equivalents. Okay. So again, the equivalent is just a mole of charge, basically. Okay. For example, if you had 1 mole of 3 plus iron molecules, you're going to actually have 3 moles of positive charge, if that makes sense. Okay, so you have 3 equivalents. So typically the IV fluids that you'll see have very small concentrations. So you use this, these units are generally the most common, milli equivalents per liter. Okay, so for example, if you had 54 times 10 to the negative third moles of sodium plus in 1 liter of solution, you would have 54 milli equivalents per liter, right? All right. So we'll talk about doing some math and conversions on these as well coming up. So try and do this, go ahead and use some of that information that we just talked about to try and answer this question here. All right, so the question says, how many equivalents of positive charge are in a solution containing 19.5 grams of sodium sulfide, okay? So we can start with grams. Probably haven't seen this kind of question yet, but so we have 19.5 grams of sodium sulfide, okay? And then again, to go to equivalents, we need to know how many moles of charge there is, right? A positive charge specifically in this question. So if we use the molar mass of sodium, I believe it's 23. 23 grams of sodium for every 1 mole of sodium. Oh, sorry, back up. So first what we need to do, 19.5 grams sodium sulfide, okay. Now we need to go from grams of sodium sulfide to moles of sodium sulfide. Moles of sodium sulfide. Okay, so we take the grams of sodium sulfide. I'm just gonna pull up what the molar mass is here. Okay, so 78.07. Sorry about that. So it was 78.07 grams of sodium sulfide for every mole of sodium sulfide. Okay, so now we can go from, now that we're in moles, we can convert from sodium sulfide to sodium ions. So for every 1 mole of sodium sulfide, we have 2 moles of sodium plus molecules when it dissolves, right? Because you're going to take sodium sulfide, stick it in water, and you're going to get 2 sodium ions and a sulfide ion, right, when they dissociate. So for every 1 mole of sodium sulfide, we get 2 moles of sodium plus, okay? And then that basically gives us our equivalents, right? Because for every 1 mole of sodium plus, we have 1 equivalent, okay? So you can see the calculation done here a little more clear. Running all that through your calculator, you'd get 0.50 equivalents. So if you're thinking about this in like terms of the stoichiometry map, so we can go from grams of A to moles of A, and we can go to moles of B, okay? And then we can go to equivalents of B, right? You can imagine this, input it on that map. It's getting really big, so I'm not putting it on the slides every time, but from grams of A to moles of A is going to be our molecular weight. And remember, A here is our sodium sulfide, B is going to be our sodium ions, okay? We can go from moles of A to moles of B using this conversion here. This would be the mole ratio. And we go from moles of B to equivalents of B, basically just using the definition of equivalence is kind of what we're doing. So moles of B to equivalents, using the fact that 1 mole of sodium plus ions is equal to 1 equivalent, and that's how you get equivalence in the end. Okay. So this problem would take you a little step further. So go ahead and try this. It says, what is the concentration of positive charge in milliequivalents per liter if you dissolve 0.29 grams of sodium chloride in 100 milliliters of water? Okay. So go ahead and pause it and try this one on your own. Okay, so this should be, at least to get the equivalence, it's very similar to last time. So you're going to go from grams of sodium chloride to moles of sodium chloride using the molar mass. You can use the mole ratio then to say that for every 1 mole of sodium chloride, we're going to get 1 mole of sodium plus ions, and then use that definition of equivalence to, this would take you to the number of equivalents, okay? And, oh, the final answer needs to be in milliequivalents. And then you can say 1 equivalent is equal to 1,000 or 10 to the third milliequivalents, right? And that tells us that we have 5 milliequivalents of positive charge. Okay. All right, but we're not done. You can tell that the problem wants it in units of milliequivalents per liter. So now we need to just simply divide by the total volume, so we get milliequivalents per liter. So 100 milliliters is equal to 0.100 liters, right? Run that calculation and you get 50 milliequivalents per liter with your units, and you got the answer. So hopefully that's making sense. I think this makes sense. Hopefully, where you're saying that 1 equivalent is equal to 1 mole of positive charge. Then you're just converting it from equivalents to milliequivalents. And then if you're asked for a concentration in the units that you're given are milliequivalents per liter, you're going to need to divide by liters to get that concentration, basically. All right, let's go ahead and do this last quiz. And hopefully this question really nails down if you're understanding the equivalence thing or not. Okay, so go ahead and try it, and if not, that's fine. We're going to work through it afterwards. Okay, so the question says a solution contains 40 milliequivalents per liter of chloride and 50 milliequivalents per liter of hydrogen phosphate. What is the concentration of sodium plus ions if sodium is the only positive ion in the solution? Okay, so the part at the end that just says sodium is the only positive ion in the solution is basically saying all positive charge in the solution is going to be credited to sodium, basically. All right, so you have 40 milliequivalents per liter of chloride. And so again, remember that milliequivalents is like a quantity of positive charge or a quantity of negative charge. So it really doesn't matter that the question says chloride. I mean, this is just telling us that there's 40 milliequivalents of negative charge, okay? So this is going to be our negative charges, I guess, negative charge. So we have 40 milliequivalents of negative charge that's attributed to chloride. Plus we also have 15 milliequivalents of negative charge per liter that is attributed to the hydrogen phosphate. And the part that I think can be confusing is that the chloride has a 1 minus charge and this has a 2 minus charge. So sometimes people think that they're still thinking in terms of moles, basically, and thinking that the 15 should be multiplied by 2 or something like that. But it's not. That's not true, because milliequivalents, again, tells us amount of negative charge. So the chloride gives 40 milliequivalents of negative charge, and the hydrogen phosphate gives 15 milliequivalents of negative charge. So that means in the solution we have a total of 55 milliequivalents per liter in the solution of negative charge, which means that the total positive charge again, since whenever you introduce ions into a solution, you're introducing it in a neutral ionic compound, right? We talked about how all ionic compounds are neutral. So the total positive charge is going to equal the total negative charge. So that means that the total positive charge in the solution is going to be 55 milliequivalents per liter. And since sodium is the only positive ion, then the concentration of sodium plus ions would be the 55 milliequivalents. Okay. So if you're struggling with this, I'm not going to go through. I mean, there's a lot of examples I probably could go through, but work through the homework and come to office hours if you have questions on that still, and we can work through it. I think this question does a good job of teaching kind of the difference, or teaching the real meaning of equivalence, where it's really just talking about a certain amount of charge, basically, is what's going on. Okay. All right. Anyway, that's just the slide going through it. Okay, good. That's the end. All right, so this lecture was pretty brief. To sum it up, it basically just talked about the definitions of strong electrolytes versus weak electrolytes versus non-electrolytes. And then in the coming lectures, we will go over exactly how to figure out what is a strong electrolyte or weak electrolyte or non-electrolyte. And then we talked about the definition of milliequivalents and tried to do some problems using that. So anyway, yep, work through the homework, and please come to office hours or email me if you have questions. Don't just like get frustrated and sit there and keep trying something. It's good to keep trying, but if you're getting frustrated, come to office hours or the virtual TA lab or Promota's office hours, and there should be plenty of opportunities at this point to where you can get help with these questions and not have to like get frustrated while you're working on them. Okay, so all right, we will chat with you later.